Hello there, this is Dr. Henry, and we're going to go over how to calculate empirical formula. And remember, empirical formula is the simplest formula. It is the kind of formula that you get from experimental data, and the ratio has been reduced among the subscripts. So, if I can get this to go forward here, here we go. So, the first step in calculating empirical formula from percent composition data is really just the step that you can do in your head. So we're going to assume that we have 100 grams of our sample. So we have an unknown compound that's 78.1% boron, 21.9% hydrogen. So when we assume that we have 100 grams, what's 78.1% of 100? It's 78.1. So we have 78.1 grams of boron and 21.9 grams of hydrogen in our unknown compound. So that's the first step. And you really you look at the percentage and just write down the grams. The second step then, and this is a key step because you can't compare the amounts of the elements in the compound when they're in grams. You can only do that when they are in moles. So we have to convert the grams of each element to the moles of each element. So let's convert 78.1 grams of boron to moles of boron. And then we know in 1 mole there's 10.81 grams of boron. So we have 7.22 moles of boron. Now we need to do the same thing for hydrogen. So we have 21.9 grams of hydrogen. We know in 1 mole of hydrogen, there's 1.01 grams of hydrogen. So we have 21.7 moles of hydrogen. So this gives us the mole ratio, and these are the subscripts for the chemical formula. So we have a mole ratio of 7.22 moles of boron to 21.7 moles of hydrogen. And that ratio is used for the subscripts. So here's our formula. And if you look at this, right? What's wrong with this formula? Can we have a formula that looks like this? And of course, we can't have a formula that looks like that because we can't have parts of atoms, right? We can't have 22 hundredths of boron. We can't have 7/10 of hydrogen. This needs to be a whole number ratio. So we need to figure out a way to make this ratio whole numbers. And the secret to this, and this is the third step, is to convert the mole ratio to the smallest whole numbers. What you want to do is divide each of the numbers of moles by the smallest number of moles. All right? And that's kind of, once we look at it, you'll get it. So what's smaller, 7.22 or 21.7? Well, it's 21.7. Wrong, right? Sorry. I'll pretend like I did that on purpose, but that was an accident. 7.22 is smaller. So we need to divide both of these by 7.22. So this, of course, will be 1 mole of boron, and this gives us 3.01 moles of hydrogen. Now, if it is a few hundredths off of a whole number, all right, and remember hundredths is the second position past the decimal point, then because of rounding, because of experimental errors, then we can round this off to 3. But if it's more than a few hundredths, like, 6, 7, 8 hundredths, you're getting pretty close where you can't round it off. And we'll see this come up in another problem. But 3.01, we can round off to 3. So here's our empirical formula, right? The 1 goes here. We don't write subscripts of 1. The 3 goes here. So here we have boron trihydride. So that's the 4 steps to finding empirical formula. Let's look at another problem. Now, sometimes instead of getting the mass composition, or actually sometimes instead of knowing the percent composition, we know the mass composition. So let's say you had a 10.150 gram sample of a compound known to contain only phosphorus and oxygen. And we know that the phosphorus is 4.433 grams. What's the empirical formula? All right, so once again, the first step is convert the percent composition to mass composition. Now, we can skip this step because we're already starting with grams. If you're given grams, don't go back to percentage. Just start with the grams, and we need to convert those to moles. So we want to convert 4.433 grams of phosphorus to moles of phosphorus, so it's 0.1431 moles of phosphorus. All right. And then let's convert the oxygen. Now, we had, I think it was 10 point something grams of oxygen total of this compound. We knew that sorry, I got to go back. We knew that 4.433 grams of that came from phosphorus. So if you take that, the total mass of the compound minus the grams of phosphorus, you get 5.717 grams of oxygen. And then we want to convert this to moles. So 0.3573 moles of oxygen. All right, now, here's our moles of phosphorus. Here's our moles of oxygen, but we need whole number ratio. So we look at these. Which of these two is the smallest? So 0.1431 is the smallest. So we're going to divide both of these by 0.1431. So of course, we're going to have 1 mole of phosphorus, and then we have 2.4597 moles of oxygen. Now, this is 5/10 or 0.51 away from 3. It's 0.497 away from 2. So this is not off from a whole number by just a few tenths. So if it's off by more than 5/6 tenths of a mole, hundredths of a mole, you're going to have to do one more step. So here's what we're going to have to do. We're going to have to find some number that we can multiply these by to get whole numbers. And if you look at this, 2.497 is really, it is very close to what? It's very close to 2.5. So what times 2.5 will give us a whole number? Well, it's a half, so 2 times a half will give you a whole number. So let's try 2. And sometimes start at 2 and then go up. If you have trouble doing the math in your head, just go through every one until you find something that gives you a whole number. So 2.5 times 2 will give us 5 moles of oxygen. And then if we multiply oxygen by 2, we have to multiply phosphorus by 2 in order to keep the ratio the same. Because remember, if you multiply every number in a ratio by the same number, the ratio stays the same. So we end up with a formula then of P2O5, so diphosphorus pentoxide. And that's how you find empirical formula. If you have any questions, please ask for help. Come in before school, after school, during lunch. We'll get you straightened out. Thank you.